Okay, let me practice more for my oral English. Today I want to introduce this paper, Active Learning and the ImageNet Scale. It's in archive. I think it's not published yet. The authors are from the Maryland or Minnesota University. College Park. I know it's College Park. College Park. And this one New York University and National Institute of Health. Mm. Okay, summary, but I'm not sure how much you know about the active learning. Uh, so we know that active learning, we have a small labeled set, and we have a large unlabeled labeled data set. Then we need to select samples from the unlabeled dataset. We need to select some or one from it. Select the most useful. Never mind it's informative or representative, but yeah, they should be most useful. Improve the performance, the largest, improve the more, have the best performance improvement, the most performance improved. So select those samples, then add labels. Add labels, finally, yeah, let me, well, I don't like it. To add back to the labeled set. Now the labeled set is enlarged. It has more samples, so it can train the model again. It's not a semi-supervised learning. It's active learning. It's need add samples by human, and this pipeline will do it again. Uh, for several rounds until we achieve our budgets. Because add labels, we need to spend money, right? Need to spend money uh, to to for labeling. So the most important part, the critical part, is how to determine the useless useness, not useless, useness of the samples. I won't introduce too much. For example, maybe like corset, and in this paper they use the distance to decision boundary as the first they define this one, and we know this definition is find a minimum perturbation to make the prediction different. The x plus epsilon will be different from the x itself. It's very common in adversarial examples, especially for the deep four. Deep four, but we know it's very hard to compute adversarial examples, or it's very hard to find the minimum epsilon on the pixel space. So they consider to move it to the feature space. It's much simpler, much simpler. Then the second problem is they found the active learning algorithm uh, have a tendency to heavily sample from the preferred samples classes while nearly ignoring others. For example, ImageNet, it contains like 1,000 categories. You should know that, right? Then preferred classes maybe just like 10 to 100 classes. So every iterations, every round, the active learning will sample from this 10 to 100 sample classes, and the remaining 900 hundreds categories won't be sampled. Then we know the labeled set will become a very biased data set. So the performance obviously will be not good. But why it's what happens in the preferred classes? Maybe it's also a interesting problem how to evaluate why those categories are easier uh, to be sampled as never mind. But so for this problem, they just propose a balanced decision boundary, balanced distance for between the classes. So you can see for this one, x is not related to the category. So every time it's randomly sampled, we don't know the information of category. Now we add a constraint. We use a strategy. First, we select the we uh, we need to define give a class give a specific class. So the function is x and c. First, we need to make sure the samples are uniform selected between classes. So for each class, we will select uh, some examples. Maybe for one batch, for for a new batch, we need to select 1,000 images. Then we have what like C5 100, it have uh, 100 classes. Then for each class, we will select 10 samples. Yeah, so it's another problem is that this one for ImageNet, it need to consider the batch size. Batch size is a new problem, but we can we it's I'm not sure if this paper consider it or not. Yeah. Okay, but the basic idea is that we need to make sure the every class we will select the top K. And then for each class, how we define the top K is also using the decision boundary, but now it's the X true of the C, namely find the closest top K closest sample to the decision boundary from both sides. Both sides. What does it mean? Both sides. First, it can, yeah, the fx can be c, and it can also be not c. Therefore, if the fx it is c, then we need to find a epsilon, a smallest epsilon, to make the prediction not c. And if the x is not c, for example, okay, if it's not c, then we need to find the perturbation to make it to C. Then we can first show this example. We use this example. So for this class C, right? We need to find some samples. First, if a sample is C, then we want to find the margin, the distance to the decision boundary, make it not C. And for some other examples, we also need to compute the distance because uh, when the f when it's not belong to C, then when these images, the perturbation will goes to here. It can also be considered as the useful images. Yeah, and of course for this one it's a C, and for this one it's not C. It's maybe B. This one B, and this one is A. But we use the decision boundary here. We consider the distance. Okay, so this is the very basic idea, and very clear and very easy. But they are the first to have a much better performance on the ImageNet scale. They also consider another thing is that the self-supervised pre-training, namely Moco and Sinclair, they use those uh, unsupervised learning, and you can see when they don't use the self-supervised pre-training, then previous active learning method can have a slightly improvement than the random select. But when it's at the self-supervised pre-train, the random strategy is much better. It's even better than the adversarial method. So that's a problem. Yeah, and yeah, I think it maybe have more relationship to some to some important question because the margin is very important in deep machine learning and and deep learning. Okay, so this figure it shows their performance. Their model's performance is the best. However, yeah, how many curves here? It's, it looks like it contains three colors. Uh, this one, the base, blue one, and here we can see it's orange, right? And why this one is also this one red, and it looks like here is contains a badge. I'm not sure what happened in this curve. It's really hard to distinguish between each other. Okay. So another problem is that how they compute the distance, how they really compute the distance to the same boundary because in their paper in their code they didn't describe the PVD, they just used a, a sentence. Computing DDB in feature space reduces to its equivalent to computing the projection of the feature vector onto the normal vector of the linear decision boundary. But this problem maybe is not very clear for uh, to read. Yeah, we can use these formulas to have an idea. So first, the feature vector is h extract from the feature. We know the CNN is first extractor, then they get the H, and they have a final linear classifier, and it will return a Z. Z then is goes to the source max, and it will give us the probability vector. So here, this one is H equal to feature of X. Then compute the logits namely times the W. So it's Z almost equal to W times Z H plus B. Or, or you can also ignore this bias term. So this one is W times H times the cosine of theta. Now the problem is that uh, its projection of the feature vector H here uh, onto the normal vector. So yeah, it's W H cosine. It's almost correct, but normal vector of the linear decision boundary. So this W should be normal. That's my thinking. So it uh, yeah, this is theta and make it to be one. So it's here this part. And we can check this one, the decision boundary. We can suppose the W is here for this category and W here, W here. So for some examples, it may be someplace, uh, yeah, but it's still different from the still not the descent boundary, right? The descent boundary is like here. This is the center, is the W. How to compute the descent boundary is still, yeah, you should check more from the code. Okay. Furthermore, I think it's have a have more have some relationship between these methods, semi-supervised learning, flex match, and the curriculum learning. And also, yeah, let's talk about it. The self-supervised learning. When they use self-supervised learning, why they have how to define the boundary, why they have a boundary, why they not have a boundary. It's also a problem. Okay, so that's it.